So this week is about the atmosphere. So the last kind of chunk of the course that we have left is the atmosphere, weather, and climate. So we'll tackle those this week. The first part of that will be introducing the atmosphere, some of the properties of the atmosphere, the layers of the atmosphere, and then we'll talk about what air is, how air behaves, and then use that to set up weather systems. And once we understand weather systems, we'll be able to understand climate and climate change. So the final week of the semester kind of ties together nicely, in my opinion, in terms of the flow between the three separate areas of focus this week of the atmosphere, weather, and then climate. Let's just quickly define the atmosphere. You're breathing it in and out right now. You're breathing in part of what we call the troposphere, which we'll talk about in a second. But the atmosphere is just going to be the thin envelope of air that surrounds Earth, and it has a lot of different protective properties, which we'll go through in a second. So you can see the atmosphere from outer space. The image or the film that's playing through here on the bottom left, that's just images from the International Space Station, and where it's flying, basically you can see the northern lights and you can see light pollution, but you can see the thin envelope of gas that surrounds Earth. So there's different layers of the atmosphere, as we'll talk about here in a second. Where in the troposphere, there's the stratosphere, the mesosphere, and the thermosphere. So all of these make up our atmosphere. So let's talk about what air is first. So what do I mean by air? What do I mean by the atmosphere? So if you take a sample of air of what you're breathing in right now here at the surface, it's going to be 78% nitrogen and about 21% oxygen. So that's the main composition. There's more nitrogen in the atmosphere than there is oxygen. And then the other 1% is a bunch of other gases like argon. Carbon dioxide is now 0.042% of our atmosphere. Methane, nitrous oxide, so we have greenhouse gases as well. So in addition to actual gases in the atmosphere, air also contains things called particulates, which is just like soot or ash. If you have a wildfire and you have ash or soot in the atmosphere, dust, mold, spores, pollen, those are all called particulates. And then we also have aerosols as well, which come from like deodorants and hairsprays and things like that, and coolants and refrigerants. So has our atmosphere always been the same? The answer is no. So this is kind of a depiction of the atmosphere from its early atmosphere when Earth started cooling about 4.5 billion years ago or so up to the present day. So if you look at it, modern or ancient Earth would have looked more like modern day Mars or Venus in terms of the coloration of Earth. So here's your first quiz question for this lecture. So you have this graph here that I want you to interpret. So it's showing you over time, so billions of years in geologic history. So the present day is right here on the right side in what we call the Phanerozoic era. And then the earliest part of Earth's history is called the Hadean period. But anyway, it's from 4.6 billion years ago to 4.0 billion years ago. And then this is looking at the total composition of the atmosphere in terms of what gases you can see in the atmosphere. So the first question is, which of the answers best describes the composition of the atmosphere of Earth 4 billion years ago? So what you need to do is kind of look here vertically at 4 billion years ago and then decide kind of the distribution of the gases that you see in the answers for the question. So questions 2, 3, and 4 are based on this graph that we have here. So our y-axis here is oxygen percent in the atmosphere, and then we have millions of years before the present. So this is a billion years, 500 million years ago, and then present day is on the right side at 0. So question 2, at what time do we see the oxygen content in the atmosphere begin to increase? Question 3, why do you think oxygen levels increased around the time that they did? And then question 4, is the oxygen level in the atmosphere today the highest that it has ever been? So again, feel free to pause, come back when you're done with these 3 questions. So let's talk about the structure of the atmosphere. So the atmosphere has layers, and if we kind of work from Earth's surface outward, that's what we'll do. So it starts with the troposphere, then we have the stratosphere, the mesosphere is above that, the thermosphere is above that, and then finally you reach the exosphere or outer space. So if we're defining what our book lists as outer space, it's something called the Kármán line. So it's an arbitrary 100 kilometers above Earth's surface. That'd be about 62 miles above Earth's surface, is when certain atmospheric scientists would say that they're now in outer space. It's arbitrary, so Some definitions go up to about 300 miles above our heads would be outer space. So it kind of depends on what source you look at. What I also want to point out is that most of the gases that we actually have in the atmosphere are going to be within 20 miles of the surface. So the higher you go up in the atmosphere, the less air molecules there are to breathe in the first place. So we're going to start with the closest layer to Earth, and that's the troposphere. So you are breathing in and out air in the troposphere right now. So this is what we interact with on a daily basis. Most planes are going to fly either right at the top of the troposphere or go slightly up into what we call the stratosphere or the stratopause. But all of our weather systems are contained in the troposphere, all of the clouds that we have, all the air pollution, 3/4 of the total actual air molecules that we have on Earth are going to be found in the troposphere close to the surface, and it's the most dense layer. So the most dense layer should make sense. If you think about air, things that are dense, they sink. So if we're talking about the troposphere, which is the closest to the surface, it makes sense that it's the most dense because it has the entire weight of the whole atmosphere pushing down on the surface. So the troposphere is the most dense air that we have. So if we go a little bit up, the next layer up, so we'll talk about the troposphere a lot more with weather and climate, so we'll elaborate on that much more. But if we go one layer up, for about 6 to 30 miles of altitude or 10 to 50 kilometers, now you're in the stratosphere. So sometimes planes will fly at the base of the stratosphere, and if you've ever been on a plane, there's occasionally times where you'll be above the cloud layer, which is pretty cool to see. So important things about the stratosphere is that the stratosphere contains ozone, and it's a good thing. So stratospheric ozone is a good thing because you can think of it as kind of like the sunscreen of Earth. So what it does is that when the sun has radiation, and that radiation is kind of a form of energy that bombards Earth's atmosphere every minute of every day, what the ozone layer does is it absorbs ultraviolet light. So when you put on sunscreen, for example, you're putting on a substance that blocks ultraviolet light, certain types of ultraviolet light, not all of it, from making contact with your skin. The ozone layer is basically a gigantic sunscreen layer for Earth, and it blocks a lot of ultraviolet radiation. So if we didn't have ozone in the stratosphere, less ozone in the stratosphere would have higher rates of skin cancer because you have more ultraviolet radiation that gets down to Earth's surface. So if you ever heard about the hole in the ozone layer, it doesn't mean an actual hole. It just means that it's thinner than its normal thickness. So the image that's playing through here basically on the bottom is showing you the concentration of ozone in the southern hemisphere over Antarctica from the early 1979 up to 2014. And it's kind of plotting how the ozone hole, or where it's less thin, has depleted and then started to recover a little bit in more recent times. So what caused those holes in the ozone layer is something called a chlorofluorocarbon, CFC. It's kind of a refrigerant or a chemical that destroys ozone. Anyway, so that ozone hole has been slightly recovering recently, but not as much as scientists would like. All right, so the other thing I want to point out is that when the ozone layer absorbs ultraviolet radiation, it tends to heat up. So it has a very specific property where the stratosphere actually gets warmer as you go higher up into the stratosphere, closer to outer space. But the reason for that is because it absorbs ozone and it kind of traps heat up in the stratosphere. All right, so based on that description that I just went over, question 5 on your quiz. So why is ozone a good thing? If there's less ozone in the stratosphere, how might that affect human health? All right, so feel free to pause, return when you're ready. If we go one more layer up, we will be in the mesosphere. Meso means middle. So this is the middle sphere. It's 30 to 55 miles up or 50 to 90 kilometers up in altitude above your head. There's not too much that's super interesting about the mesosphere. So the main thing is that objects from space burn up here. So if you ever see meteor showers or things like that, you're seeing stuff burn up in the mesosphere. So that's kind of the main takeaway about the mesosphere. Finally, if we go up to the thermosphere is basically above 55 miles in altitude, and then depending on the definition that a textbook follows, that might go up to about 62 miles above your head, or it could go out to like 300 miles. So it's a very subjective definition. But the thermo is heat, so a thermosphere is heat sphere. So this is another layer that basically it gets warmer the higher up you go in that layer. And part of the reason, again, is that because Earth is constantly being bombarded by radiation from the sun every minute of every day, our thermosphere absorbs some of that radiation. And if this is confusing to you, I will talk about this in a couple slides, not a couple slides, in the next set of lectures to help clarify what I mean by radiation. So the thermosphere blocks certain types of radiation from the sun. It blocks X-rays and it blocks gamma rays. There is only a certain amount of X-ray radiation that you should be exposed to in your lifetime, because if you have more than that exposure, it tends to cause mutations in your DNA. Same thing with gamma rays. So your body is not supposed to come into contact with gamma rays because it mutates, it causes genetic mutations and changes to your DNA. So the nice thing about our thermosphere is that it acts as another protective layer, and it blocks X-rays and gamma rays from reaching Earth's surface and filters them out. So other things about the thermosphere, if you've ever seen the northern lights or the aurora borealis, they are in the thermosphere. So if you ever see them, you know that they're at least 55 miles up above your head. And then the International Space Station is about 217 miles up. And then all of our satellites, or almost all of our satellites, are orbiting in the thermosphere. So if we put all that together, again, the troposphere is at the closest to Earth, what you're breathing in now. The stratosphere is above that. It has the ozone layer that blocks ultraviolet radiation and prevents higher rates of skin cancer. On Earth, we have the mesosphere, middle sphere. Meteorites burn up here. So M, meso, M, middle, M, meteorites. Then we have the thermosphere, northern lights. Technically, that's when we kind of get into outer space. That's where our satellites are as well. That's what blocks X-rays and gamma rays and harmful radiation as well. And then you're in outer space. So that should be it. You should be able to finish up your quiz questions, and then you'll return for the next set of atmosphere lectures.